Okay, so last month we had a great presentation by Jeff on NVIS, and as part of his presentation, he talked a lot about propagation and these diagrams where you see these lobes and mathematical looking, scientific looking things, which kind of went over my head. I kind of get the idea of what's going on, but I have no idea how to make or interpret or what's going on with those diagrams. They're important to understand, important for our hobby, but there's some background there that just I don't get. So we have a presentation tonight by Orion AI6JB, who's going to talk about antenna modeling and fill us in on how all that stuff works. So Orion, over to you.
All right, thank you, Greg. Yes, antenna modeling. It's one of those things that seems to be kind of like voodoo, and it's always fun to listen on the radio and read articles about what antennas can or can't do. So this came up in, I think, a coffee break discussion about antenna modeling. So I thought we would go ahead and put together a little presentation on antenna modeling. Well, in a nutshell, antenna modeling is simply a computer software program that approximates the performance of the RF antenna. I say approximates because it's not going to be accurate. Things such as the soil conductivity that's underneath your antenna will have a lot to do with it. Propagation, of course, is part of it. Plus any other metal, trees, things that are around your antenna are going to affect the performance of the antenna. But in an entirely theoretical world where there's none of that stuff around and you have perfect ground, or you can approximate a less than perfect ground, antenna model will give you that performance or let you know what your antenna is going to do. Now, even though it's an approximation, it's still going to give you a pretty good idea of how it's going to perform. You can pretty much bank on the fact that, if you change the height or you change the length, you change the configuration of your antenna, it may not get you, it may say, the model may say 10, you're going to get, 10 dB out of it. And in reality, you may only get 8, but it's going to be better than the other configuration where the model says you're only going to get 8 and you'll only get 5. So it's an approximation, gives you a rough idea. But what's nice about it is you can run it in a computer and you can tweak it and play around with it and get a sense of what's going on with your antenna and go from there. So what I thought I would do is first dazzle you and wet your juices about what an antenna model can do. So let's just take the simple 80-meter T-top dipole. And in this particular model, I used an 80-meter at 3.5 megahertz. And I put it at about 135 feet above the ground. And that is roughly about a half a wavelength. So the first thing the model will do for you is give you basically a graphical look at what the model is going to look like. So you can see right here, you've got your, hold on a second here. Let me get the laser pointer out. Okay. So right here you can see right here the dipole antenna, and this little guy in the middle, that little blob right in the middle, that circle, that is the feed point of your antenna. So the first thing you do is it's going to give you a nice little picture about what your antenna looks like. Then when you hit the calculate button, you then get this chart that Greg so eloquently put. This is a radiation pattern. Now, there are a couple key things that are nice to know about this radiation pattern and what it'll do for you. So first of all, up in the left-hand corner here, you'll see that it says, hey, 3.5 megahertz. You look over here, you're looking in the vertical plane. So if you have your radiation pattern and you slice it up and down, this is what the pattern's going to look like. It also tells you down here in the lower right-hand corner, it says, hey, what is your maximum gain? Well, the gain for this antenna is going to go from minus 999, basically infinity dB, to plus 7.67 dB. Now, you notice it says dBIC. Well, dBi is a theoretical concept where you have this physically impossible situation where you have a itty bitty little point, and all the dB is calculated on that. It's purely theoretical. It'll never happen. But we can make it practical by saying roughly, if you take this 7.67 and you subtract 2.1 dB from it, roughly about 5.5 dB over a dipole is what the gain will be on this antenna. And that's just, like I said, again, it's approximation. And also down here, this shows you the file number or the file name of the antenna that I have. So now this gives you the pattern. You can also click another little button, and what will happen is it will calculate the point of maximum gain. And in this case right here, the maximum gain is 7.67, which we saw down here in the bottom right. But we can see that it's at 61 degrees. So here's 90, and you have 61 degrees. So roughly about 29 degrees above horizontal is where your maximum gain is going to go out. Then you can see from here you have a 42, and you have, I don't see the other number here, but you have the beam width of 34 degrees. So you're going to have, what was that, 17 degrees up and 17 degrees below this 61 degrees. So you have a beam width of 34 degrees. And as you start going higher up, you can see and follow the trace back that right about here, at looks like just a little less than 30 degrees, you have 0 dB gain on your antenna. And after you get down to 90 degrees, you actually have attenuation. You have minus dB here. And again, as you get closer and closer to horizontal, you see that your gain goes to 0 or infinity negative. So this gives you a really good representation of how the pattern looks in the vertical plane. Well, there's two planes. There's vertical and horizontal. Let's take a look at the horizontal plane. Here we have the same antenna, which is 130, an 80 meter dipole at 135 feet. And we can see here, let me get down here, we have again the maximum gain at 7.67, and it goes to a minimum of only minus 1.9. So not a whole lot of attenuation. It's still good, but not a whole lot. We can here now see that our antenna in the broadside position, so here's 0 degrees, at 90 degrees to our antenna, and to be specific, at 91 degrees, we have our maximum gain of 6.7 dB, and that's dBi. Bandwidth is 88 degrees. And so you can see from all the way from, what is that? I can't see what that number is underneath there, but what is that? Like 130 to 45 degrees. It's probably 135 to 45 degrees. You've got most of your power going. Oh, I forgot to mention these dots right here. These are the 3 dB point, meaning 3 dB down. So from the 7.67, take away 3 at 4, you're going to have a gain of 4.67 here. And the significance of 3 dB is that's half power. So now you've lost half the power between here and here. So most of your gain is in this area. And again, we can also see now what happens on the backside of our antenna. And here it shows the maximum gain on the backside of our antenna, same gain, but it's at 271 degrees from the broadside of our antenna. And the bandwidth is 88 degrees, same as the front. So that's the horizontal panel. So that'd be like taking a slice in the horizontal plane of your antenna. That is the horizontal and vertical graphs of the antenna. Are there any questions so far? All right. The model will also generate some good juicy information about your antenna. And again, I'm hoping your screens can see this. but let's get the old laser pointer going. And first thing that you'll want to see is it'll show you the impedance. Oh, let me back up a little bit here. This shows you how much the input power is into my antenna. So in my model, I said we're going to put 100 watts into it. Here you can see up here you can see the frequency 3.5 megahertz, and it's a wave. The length of one full wave is 85.66 meters. Here's the file name, and here you can see the impedance at the feed point at this frequency. So we've got an impedance of 66.5 minus 29.7 ohms. And probably what most of you are interested in is what is the SWR of that antenna at the feed point at this frequency, and it's 1.79. Again, this is an approximation. Things such as trees, other steel, metal, ground will have effect on what that SWR is, but you can pretty much know that, hey, you're below 2 and you should be able to run pretty good. Let's see what else we have here. We have radiating power, tells us it's going to put out 100 watts. And, oh, you can actually see the current and voltage on the line at the feed point. And so what you'll see here is the current is 1.23 amps at 0, and you got your voltage here at 81 volts. Now, one of the things that I love about antenna modeling is I am a visual kind of guy, and I like to be able to see things in 3D, and that is what the model can do. And what you see here is a 3D model of what the radiation pattern looks like. And you can see right here, the red, this is where your maximum gain is. And the blue right there in the middle is your minimum gain. And you can see that most of it's coming out broadside to the antenna, because the antenna is right up here. You can see it up there. There's your feed point. And you can see that the most of the power is coming right out through there. Very nice pattern, and this makes a pretty good DX antenna. If you want to know what the dB rating, how much dB is, you can see there's a scale here on the side. Let me see if I blow that up for you, and you can see that a little better. You can see it gives you the dB. So remember we saw that 7.67. The light purple or the magenta is the one that's going to have the 6.7. And you got minus dB here with the 30, so that's a pretty good attenuation for an antenna. Also, some of the things we might want to know is, hey, if we've got a doublet up in the air, which is a favorite of Brian and I, where is my antenna resonant, and where is the SWR going to be the lowest? And guess what? That's what this thing will do. It will produce a chart that shows you the impedance. Let's see if I got the right one. No, this is the SWR, excuse me. This is the SWR chart. And we'll blow it up a little bit here. And you can see that there's numbers on the left here. 1, 2, 3, 4, 10, 20. That's SWR. And anything under 2 is good. So you can see here at 80 meters, we are at 1.63 SWR. Now, you can also see that as we get towards up here at 11 megahertz, which isn't anywhere near one of our privileges, we have another dip just over 2. The thing that is interesting about this antenna, which we use with tuners all the time, some of the highest SWRs are on the 20 megahertz band, or on the 40 meter band here. And if you look at 20 meters, they're all up in here. So the tuners are actually doing quite a bit of work for if we're going to use this antenna as a multi-band antenna. If you're curious about impedance, that's what the top chart is all about. It will show you the impedance, and it gives you the real version, and it gives you the imaginary portion of the impedance for the antenna as we move through the frequency. So you can see here we have down here at 3.4, you can see the real part goes up and down, and the imaginary part flips back and forth. Downstairs, or I should say the bottom part of this chart, gives you the impedance, the complete version of the impedance plotted against the phase of the current that is flowing. Oh, is this current or is this voltage? Sorry about that. I don't know which one that is, but anyway, it shows you the phase. I don't particularly use this one very often. Now, if you are a Smith chart fan, the program will create a Smith chart of this antenna as it moves through the different frequencies. So you can see the SWRs for that as well. So in summary, what can it do? Well, it can plot vertical and horizontal radiation patterns. It can calculate your maximum gain. It can show the direction of where your maximum gain goes. It can show you the 3 dB bandwidth. It can give you a 3D representation of the radiation pattern. You can plot SWR and impedance over frequency range and see where your antenna has its lowest SWR, and you can produce Smith charts for it. Now, we had a wonderful presentation last month by Jeff, N5JEF. And I thought it'd be kind of cool to use the software and take a look at what the software will produce based on his presentation. And what I thought we would do is we would compare his NVIS antenna to a DX antenna. So one of the things Jeff pointed out was that a good DX antenna is roughly going to be about a half wavelength above the ground. And then he said a good NVIS dipole is going to be about an 1/8 wavelength above the ground. So half wavelength for 80 meters, roughly about 135 feet, 130 feet. And a quarter wavelength is around 33 feet. So what I did is I used the model, and I did one at 130 feet and another one at 33 feet. So let's take a look at 33 feet first. So the vertical pattern looks like this. And one of the things that you might notice from what we have already seen, because we were looking at the one that had the at 130 feet, notice that the bandwidth is practically straight up and down. And as Jeff pointed out, and notice it says 0 degrees here, so the maximum gain is straight up in the air. And Jeff pointed out that in order for a good NVIS antenna to work, we want to put all the power up straight up into the F layers and have it scattered back down on top of us. So that 1/8 wavelength above the ground is definitely forcing everything up as well. One of the other things that's kind of interesting I noticed is the gain isn't quite as high. It's only 5.9 compared to what you would normally see in the full version of the antenna. So remember, we were looking at this guy here, and we had a gain of 6.7. Notice also that we had most of our power heading out at about 61 degrees versus straight up and down. Let's take a look at the horizontal pattern. Now the antenna says that the horizontal pattern is pretty much going to be omnidirectional, which is all directions.
We have a question.
Go ahead, question.
Yeah, question from Phil. Go ahead, Phil.
Okay, hopefully my microphone is working. So hey, in those vertical patterns, the element is coming in and out of the page, right? That's the way the element would be oriented?
That is correct, yes.
Okay, cool. Thank you.
You're welcome. And now here we go with the horizontal. And we're looking at, and you can see that it's a big circle. So that pretty much tells us that there's gain, the even amount of gain is one big circle. So it turns into, at the maximum gain, it turns into basically an omnidirectional antenna, which would explain why Jeff said that everything within 250 to 350 miles is in all directions is going to get us good signals. Let's see here. What else? Now let's compare that to what our antenna looks like when we were at 135 feet. And guess what? Look, it's got some directionality to it, and it's pointing in definitely in opposite direction. So you're going to lose some of the stuff at the ends of your antenna. So, okay. And what does it look like in 3D? So here you can see it. You can see all the power is heading straight up, and you can see that as we go closer to the ground, we start losing the attenuation. So that gives us an example of what the difference is between DX antenna and a NVIS antenna, and it definitely Jeff's contention that an eighth wavelength versus a half wavelength it pans out perfectly, as it should. All right. Well, another thought I had is a lot of times, Brian and I, we've for years have said, hey, higher is better. So I thought, well, let's go ahead and look at see what if that really pans out. And so what I did in this case, though, is I took a 20 meter dipole, and because it's just smaller and it makes more sense for reality to us. So what we're going to do is we're going to look at a 20 meter antenna, and let's put that 20 meter antenna at 33 feet. So 33 feet on a 20 meter antenna is roughly half a wavelength. So half wavelength shows us that we've actually got a very nice, good DX antenna. Look how it's all pulled together nicely. And we can see that we have nice focus of our power all heading out opposite or broadside to our wire. Now let's take this and let's make it one full wavelength. Uh-oh, something's happening here. So what we can see now is we have the maximum gain at 7.19 dB. So our gain actually came up from the previous one. And another good thing is that our angle of attack actually is now only 16 degrees above the horizon, which actually makes it a slightly better DX antenna. But what's interesting is, hey, we're seeing a lot of vertical components. So here, you're somewhere between you're probably 5 dB, 6 dB right here, and you're sending power up at an angle, which isn't exactly what you want when you're doing DX. So at one wavelength, the pattern seems to be doing some changes. And it looks like this in 3D. So you can see here, you can see that most of the power is being focused out there, but we also have quite a bit of the radiation pattern heading up into space. And so they call these lobes. And so we're generating another lobe. That's at one wavelength. So let's go to 130 feet, which is normally where we try to shoot for our 80 meter doublets. So that puts it roughly at 2 wavelengths above the ground. And look at what we get here now. You can now see 1, 2, 3, 4 lobes. Interesting enough, this bottom lobe, the gain actually gets a little bit higher, but the bandwidth sure shrinks. Now it's only 7 degrees wide. And our takeoff angle now is, what is that, 92? It's only 8 degrees. So in some respects, it might be slightly better, but look at what we got here. We've got these nulls in here. That means any signal that comes at us through here is getting attenuated. It's not actually being amplified. It's getting attenuated. And so anything here past this is a big blank spot. So you see these nodes, these are nulls. And so what tends to happen is you start getting fade. And so we've noticed it, that we noticed our 20, when we're on 20 meters where they're 80 meter doublets up above 100 feet, we get a lot of fade. We'll hear somebody, and then the next moment they're gone, and then they come back, and that is because we've got these nulls in here. So, question now is higher better? Well, yes and no. You do get more gain out of it. You definitely get a lot more directionality out of it. And I guess I didn't touch about directionality, but you can see that the lobes are pointing definitely in one direction, and we are definitely having a much narrower bandwidth, a beam width of our signal. We're getting lower angles of takeoff, which generally is a good thing for DX, but we're sending a lot of power up into space, and we're now starting to see a lot more susceptibility to fade. So that is what the model can do for you. You can play around with these different things and get a sense of what will happen. And so Brian and I are now starting to investigate the possibility of maybe putting our antennas on pulleys or something, so we can bring them up and down as we move around bands and things like that. So that is how you might want to use your antenna model. So a lot of neat, good things here. And by the way, I'm only touching the surface. There are optimization features. So for example, if you want to optimize for gain, you put in and say, hey, I want to optimize for gain. And you say, I want to optimize it based on length of the wire, or whatever configuration you choose. And the computer will do calculations until it comes up with the optimal criteria. You can compare patterns from one run to the next run, a whole host of other things that I haven't even touched here tonight. And so you're probably thinking, oh my gosh, why is he spending all this time on antenna modeling? There's no way in the world I can afford it. Well, good news is it's free. Well, at least one version of it is. There's a product out there called the 4NEC 2. You can get it at the www.qsl.net, or you just Google it and say 4NEC 2, and you'll find a download site. And it's free, and it's good up to 11,000 segments, or a maximum of 2 gigabytes for onboard memory. So it has to do with how much memory is actually on your computer. So if you don't have 2 gigabytes, it's going to be less. So it's free. And I was just on there the other day, and they recently updated a release on January 2020. Interesting enough, there's another product out there called EasyNEC by W7EL. They do have free software, and they have basically a trial version. You can only do 20 segments, which is great for evaluating a dipole or some simple beams. You can probably get away with 20 segments. But unfortunately, if you want any more than that, you're going to need to spend some money. That's $99. And if you want to go to 2,000 segments, you'll need to spend $149. The interesting thing is, you notice both of these have an NEC in the middle. They both use the exact same engine. They call it an engine. And that does the calculations. It was developed by Lawrence Livermore Labs. It went public domain in the 90s. And I should say version 2 went public domain in the 90s. There's a version 4 out there that's still proprietary. You can spend buku amounts of money and get that as well. So they both.
And we have a question.
Go ahead.
Yes, Dan KN6DRN asks, what is a segment?
Okay. So the way they calculate all this fancy stuff is they take the wire and they break it up into segments, and then the computer analyzes individual segments and then adds it together to produce the total pattern. So if you have a complicated antenna, you're going to need a lot more segments. So segments kind of give you an indication of how complicated your antenna can be. Does that answer your question?
Yes, thank you.
Okay. Now the difference between 4NEC 2 and EasyNEC, and I don't use EasyNEC very much, but one of the things I found is it's far more user-friendly than 4NEC 2. And when you Google and ask questions, there is a support group out there for EasyNEC, and I find that it's easier to find that information. So, if you want a lot of support, you might want to spend the money. If you're willing to dig deep and learn how to make this thing work and do a lot of trial and error, the free one works just the same. So you don't get you're not going to get a better model by actually spending money. What you get is a more user-friendly interface between the two. Now, these aren't the only two out there. There's MiniNEC and a whole host of other ones as well. Just do your research and you can pick it up. So the model can virtually do anything. One of the nice things about the 4NEC 2 product, and I'm sure EasyNEC has it as well, is they have a bunch of sample models. So and I just have fun playing with those. So have you ever wondered what a 5-element twin loop quad looks like? Well, here's one. That's what it looks like. And what does the pattern look like? And so you can see this is actually quite a complicated antenna. So you got 5 elements and you've got 2 loops, and you got your feed point right there at the driver. You got a reflector, and it looks like 3 directors. It's a VHF antenna, and here you can see what the vertical and horizontal pattern looks like. And you can see here, let me blow this up for you. This one says you get a gain of 12 dB on it, and your beam width is 50 degrees. So you get some pretty good directivity out of this one. You get some pretty good gain out of it. And another topic we really haven't talked about is this has a very good front to back ratio, meaning it rejects a lot of signals off the backside. You can see here that you actually get attenuation from signals coming in the back. So let's say you're operating here in Sacramento and you're picking up a lot of garbage from San Francisco. This is the antenna you want to use, because that group you won't hear them, but you'll hear people on the East Coast if you have this pointing to the east. So what does it look like in 3D? It actually looks pretty cool. And again, you have all the information. You can see what your impedance is. And look here, you've actually got an SWR of 1.04. So this antenna has been designed pretty well to match the 50 ohms. So you wouldn't need a tuner on this one as well. Another thing, I don't know if you noticed on the dipole, the radiation efficiency is 97. We were only getting 86% on the dipole. And if you'd noticed, as we went farther up and we created more of that fragmentation, that radiating efficiency dropped as well. Another thing that's pretty cool about this antenna is check out the SWR. Has a nice clean SWR, and you can see here anywhere in the 2-meter band, it's well below 2.2 to 1 SWR. So what can an antenna model do for you? It can show you how your antenna will perform. You can optimize it by throwing in different kinds of scenarios. It's going to save you a lot of money. If you're an antenna builder and you want to try out new antennas, you're not going to be spending a whole lot of money in the trial and the error phase to try stuff that doesn't work. You'll have a pretty good idea what it's going to do before you actually build it, which is what I do, and it's a lot of fun. So are there any questions out there regarding antenna modeling?
I have. Just wanted to share quickly that Carol had posted up, that's KP4MD, has posted on the QSL website, so www.qsl.net/ her call sign KP4MD, and then / modeling.htm. She's posted a few of the models of commercially available antennas. Carol has done some exercises that people might be interested in checking out.
Oh, very cool. Very cool. Any other questions? I'm looking through the chats here. It looks like my presentation answered a lot of the questions as we were going through.
Which one are you using?
I'm using the 4NEC 2.
Thank you.
And like I said, it doesn't have all the fancy interface, graphic user options like probably the EasyNeck does. It's actually, if you look through the user manual, it still talks about key punch cards. So you can see, you get a sense of when it was developed and when it was used mostly. So, but at least they are updating the software and dealing with software issues. Any other questions?
Orion, this great presentation. I just wanted to comment that you said that there's a lot of other variables, and one of the ones that are kind of useful is if you're going to run twin lead or 450 ohm line, you can set the default from 50 ohms to 450 and then and work there for your SWR. Also, I don't think you mentioned, but you can change the slice angle on both the vertical and the horizontal with just a cursor and with EasyNeck and with a mouse, and it's really easy to get gains at say 10 degrees if you're into DX and stuff.
Exactly. Yeah, this one can do it as well. I just didn't want to go to that level of detail. And you're right. It's very simple. You just basically point on the graph and use the arrow keys, and it will show you the different slices as you go through it.
And they're all printable.
Yes, they're all printable. I actually don't print. I just use screenshots. A lot of times when I'm trying to analyze a antenna, I just take screenshots and paste them onto a Word document, and then I go page by page for that. Any other questions?
Hey, Ryan, this is Fred.
Hey, Fred.
Hey, I know the dipole and the beam are pretty easy to understand. I like those good examples because they're very straightforward. I've tried to use the software to model my in-fed inverted L, and there isn't a sample in there for that. So is there any tricks to plotting your antenna design out?
No tricks. You just got to work out the geometry. So for example, I'm going to go ahead and throw up what can you guys see that? Yeah, I'm going to throw up what the geometry looks like for the 180 meter, the 80 meter, 135 foot dipole. So you're, like I said, when you're doing the NFED and L, you're just going to have to draw it out and then calculate the points. And one of the nice features is you can use variables. So for example, I believe, let's see, Z in my case, in my formula here, is the height, L is the length, D is the length of the dipole, and T is the width of the ladder line. And so I actually have 3 wires, and you can see I'm using 200 segments for each of the wires and 1 segment for my feed point. And you just have to work out that part of it. And sometimes the geometry is what messes me up too.
Okay, thank you. That's perfect.
I have a comment on NFED antennas. You have to be a little careful because the coax line can become a part of the antenna, and you have to model that too, as opposed to a balanced antenna like a dipole.
You know, I have never modeled the NFED, so but that's a good point. Yeah, I'm not sure what it would do, to be honest with you.
There's a few of us in the club that likes to throw up the NFED in a working portable or out of the RV. It's real easy to deploy, and it seems to perform very well. I'm actually using that as my primary antenna here, and I'm using the 80 meter half wave with the transformer on one end close to my shack, and super easy to deploy. But I can't figure out the radiation pattern on it, so I'm gonna have to work on your software there and figure that out. Thanks,
Okay,
Ryan.
cool.
Great presentation.
Well, thank you. You're welcome. Any other questions?
Good presentation, Orion.
All right. Well, thank you, everybody. And I'm going to go ahead and turn it back over to Brian.